Hi everyone, so today is section 23. We're going to talk about the Archimedean property, or AP. I might call it Archimedean principle a lot. I always forget what the P stands for, if it's property or principle, but it is Archimedean property. Okay, so let's start by defining it. Okay, so Archimedean property, or AP, says that this statement is always true, that for any real number that you hand me, there exists a natural number such that x is strictly less than n. Let's write it out in words. Given a real number x, there is always a natural number bigger. Okay, so let's go over some notes that are important for this. So first, let's quickly recall that the naturals are a strict subset of the integers, strict subset of the reals. Okay, so can use AP on N or Z. So any subset of R containing the naturals. This property is extremely nice because you can even specify if you want your natural number to be bigger than something. So say you want it to be bigger than 2. Okay, so that works even if x is less than 2. But you can't really restrict it to be smaller, because that won't always work. So like, let's say I want to use AP on x equals 2.5, but I want the natural number to be less than 2. Well, that doesn't work, right? But you could always say, but I want, so like, let's say you want to use AP on 2.5. Let's pretend like that's a difficult number that we don't really know much about or something, I don't know. So you can say, oh, but I want it to be bigger than 5 or something like that, okay? So that's allowed. So why do we use this? Well, this is a huge help proving indexed unions and intersections. I know I'm very creative with my language today. Okay, so let's try an example to demonstrate this. So let's say show, or how about this? Let's say what does, all right, so let's say what does this intersection equal, and then prove it. Like we're on the schoolyard or something, prove it. So here's another thing that I like to do is I'll say, so let's say I'm starting my work. This is maybe on an exam or something. So I'll say, let a sub x equal 3 minus 1 over x squared, 5 plus 1 over x squared. Okay, so now I don't have to rewrite that every time. So if I want to talk about, like, let's say a1, okay, that would be 3 minus 1 and 5 plus 1. And you might be thinking, well, Danica, can't you just do that in your head? And I can, but it's not going to illuminate the pattern in the same way if I just wrote 2 comma 6. Okay, so here we have 3 minus 1/4 and 5 plus 1/4. So what's happening? So on our left-hand side, we're getting closer and closer to 3. But from which side? Are we getting smaller and getting closer to 3, or are we getting bigger and getting closer to 3? Okay, so let's try to write these out. So let's let A1 be pink. Okay, so let's say that this is 2 and this is 6. So we also have everything in between. Okay, let's let A2 be blue. So we get quite a bit closer to 3 and a bit closer to 5 as well. Okay, so we're taking intersection. So at this point, all we care about is this intersection part that the two overlap in. So if we go another iteration, A3, we get closer to both of them. We have this. So now we only care about this, right? So let's think about this pattern. What are we doing? Well, we're approaching 3 and we're approaching 5. So now we need to ask ourselves, do we have closed brackets or open brackets? Okay, so what we want is closed brackets, and how you figure that out is you ask yourself, is that element in every single one of my sets? And the answer is yes in both cases. So we're shrinking in because now we don't really care about A1 anymore because A2 is included in A1. And we're taking the intersection, so we only care about the smallest one forever and ever. Okay, so we let X be an element in our intersection here. So what does that mean? Then X is in all of them, but what do they look like? So they each look like that. And so now I'm going to teach you another trick, is whenever you see an element inside of an interval, you can rewrite it as a like inequalities. So that has to be less than or equal to X, which has to be less than or equal to 5. That's 1 over m squared. For every m in the integers, that's a pretty big deal. Okay? And similarly, you can do the reverse. When you see a line of inequalities like this, you can go into interval notation. So right now we're not going to do that because I'll just get us back to where we were, but that's just a general thought for other proofs that you try in the future. Okay? Okay, so what the heck do we want? Well, we would like to say that somehow now X is in 3, actually in between 3 and 5. That it can't be bigger than 3 and it can't be bigger than 5. So how are we going to do that? Well, here, let me write what I want. So I want 3 to be less than or equal to 5, greater than or equal to 3 and less than or equal to 5. Okay, so I want that. Now, when you're faced with something that you're trying to show that your element is in a smaller subset than what you have right now, or a smaller set than what you have right now, I tend to do that by contradiction, or at least that's what I'll try to do. I can't give a sweeping guarantee that that'll always work, but that's what I typically do. Okay, so by way of contradiction, say X is not in 3 to 5. Okay, so what does that mean in inequality notation? Well, that means that, so X is strictly less than 3, right? Because it can't be equal to it, or else it would be in the set. But if we combine that with what we already know up here, then we get this. Beautiful. For all m in the naturals, for every single one. Okay, so hopefully you're starting to see like how this is kind of falling apart. So now I'm going to go over to this right-hand side, and I'm going to do some scratch work. Okay, so first thing that I do is I think about what it is that I want. So I'm just going to start with this piece here. Okay. So I want a contradiction. So I want some n in the natural numbers such that y is less than 3 minus 1 over capital N. Okay, so you might be thinking, Danica, aren't we talking about square stuff? So for me, we're going to end up that n is less than or equal to n squared, and you can make it strict if n is bigger than 1. It's just easier this way because then you don't have to figure out, well, is my natural number a square or not, like all this weird stuff. Anyway, if you do it a different way, that doesn't necessarily mean it's wrong. I want to always say that over and over again. Okay. All right, so we're trying to get a contradiction, and this is the only way we're going to get a contradiction. So, okay, so here we go. Let's start solving for n now, because we just need to figure out who this n needs to be. Okay, Oh boy, okay. So now we have this is less than 3 minus y. Okay, well, we know y is less than 3, so we can divide by it because it's not going to be 0. Okay, you always want to be very careful about 0 stuff or negatives. We don't have to flip it because it's going to be positive. Here, maybe I'll say that specifically. So 3 minus y is bigger than 0, strictly. Okay, so cool. All right, so we just need to find an n like that. Well, thank you so much, Archimedes. Then we maybe want 1 over 3 minus y is less than n squared, so that then we would have y is less than 3 minus 1 over n squared. Okay, so for this to happen, so n needs to be bigger than 1. And remember from our notes above, that's okay. You can ask for n to be bigger than 1. Okay, fabulous. So if you didn't see this right away, that like you would want to talk about n first and then talk about n squared, that's okay. But here's kind of the problem you would run into with the n squared. So you have this, but you can't just shove something in between there. But what you could do is you could square it again, but it's just, yeah. I guess you could take the square root, maybe. Oh, that wouldn't, yeah. I don't know. I wouldn't want to do anything like that. I just want to do this. Okay, so we're focusing on this part. So let's start with that. So if x, I don't know why I keep using y. Sorry, if x is less than 3, then since 1 over 3 minus x is in the reals, by AP, there exists a natural number such that, so first I want to say n is bigger than 1, and n is bigger than 1 over 3 minus x. If I scratch, then x is smaller than, oh my gosh, why am I totally blanking? 3 minus 1 over n squared. But we said x bigger than or equal to 3 minus 1 over m squared for all m in the naturals, and n is in the naturals. Contradiction. Therefore, okay, so we can't skip to therefore, right? Because we still have this other option here. So, okay, well, it doesn't work when x is less than 3, but okay, what if x was bigger than 5? Maybe it would still work up there. Okay, so you do have to address both of them, but seeing as they're the same argument, what you can do is you can say similarly for y bigger than 5. Okay, you can't use that too liberally, and just be saying similarly all over the place. But when the argument's going to be literally the same, you can. Okay, therefore, sorry, x. Geez, I keep saying y. I'm not so sure why I keep doing that. Okay, therefore, x is in 3 to 5. Meaning the intersection of this is a subset 3, 5. Woo! Okay, now if we try to do the other way, whoops, this one's a little bit quicker. So I'm going to give in and just call this y. Okay, so say y is in there. Well, we're going to use my trick of turning this into an inequality, chain of inequalities. Okay. All right, well, so let's talk about what we want. Well, we want y to be in AM for all m in the naturals. Well, what the heck does that mean? That means that 3 minus 1 over m squared less than or equal to y less than or equal to 5 plus 1 over m squared for all m in the naturals. Whoop. Beautiful. Okay, so what do we notice about this compared to this? Okay, well, awesomely enough, this is always smaller than 3.
This is the top result.
Google thought I asked it something. Okay, so that's awesome. So 3 minus 1 over m squared is less than or equal to 3. So it's always going to be less than because we can never really touch infinity, right, and get that weird 0 thing. But it's an or statement, and we actually do want like the closed brackets, okay? So we're still allowed to say that. There's nothing wrong about this, okay? It's just like you can say 2 is less than or equal to 3, right? That's true because it's an or statement. You can say 2 is less than 3, but you can say it's less than or equal to. Okay, cool. So what does that mean? That means, so for all m, we always need to specify that, not for some specific m or something. So that means that we get this. Woohoo! Oh, I always like saving the shorter ones for last. Okay, so now we're going to use our trick of reversing back. So we have a chain of inequalities, and we're going to turn that into an interval. So then y is in the interval. Okay, so a problem that I've had with students in the past is what they'll do is they'll try to say that this is a subset of 3, 5. While that's true, that's what you're trying to prove. Okay, so you can't just, so remember, we can't just say what we're trying to prove. We can't just state it. You have to actually show that. So that this is us showing that it's a subset, right? So we might not think about that in the time, but that is what we're doing. Okay. So then, since it's in all of them, by definition, y is in the intersection of all of them. So then 3, 5 is a subset of this intersection. So another thing you could do is at the beginning, you could say this equals A, and then that makes it so much easier. You don't have to write all this stuff all the time. But here we are. C'est la vie. Therefore, they're equal. Okay, have a great rest of your day.